All right, guys. So the last thing we're covering in this chapter is Descartes' rule of signs. So you're going to have to turn a few pages. We are skipping a few problems, but Descartes' rule of signs is the last thing we're covering in chapter 4. Now, for the most part, Descartes' rule of signs Now, this here is going to seem like there's a lot to it, but for the most part, once we see what we're doing, it's really helping us determine what possible solutions are we going to have. Descartes' rule of sign tells us three main things: the number of possible positive zeros, possible positive values for x, possible negative values for x, and complex numbers. How many are going to be complex? That's what it's telling us. Now, the number of possible positive real zeros is equal to the number of sign changes of f of x. So as we go from one term to the next, if the sign changes, that means one more possible positive zero. The number of negative real zeros is f of negative x's sign changes. And complex is what's left over. So if we look at this here, determine the possible number of positive real zeros, negative real zeros, and complex or imaginary zeros. We can just take f of x. We could rewrite it if we want, but we're looking for the number of sign changes for positive. Okay? We're ready for this. From x to the 6th to x to the 5th, does the sign change? Yes, it went from what? Positive 2. So that is 1. X to the 5th to x to the 4th. Does it change? Yeah, so that makes 2. X to the 4th to x to the 3rd. Yes, it went from positive to negative. X to the 3rd, x to the 2nd. No. X squared to x. No. X to our constant. No, because it's going negative to negative to negative. So how many times did the sign change from one term to the next? So the number of possible positive zeros we could have is 3 or an even number less than. So we could have 3, or if I take 2 away from 3, 3 minus 2 is 1. If I take 2 away from that, we would have what? Negative 1. I can't have a negative group of numbers. So the possible positive zeros we can have, the possible positive values of x that work for this, is I could have 3 of them, or I could have 1. That's it for that part. What do we think of this so far? Positive sign. Now we also need to do a similar thing for negative. Now for negative, we need to find all the sign changes for f of negative x. F of negative x. So for f of negative x, well, we don't have f of x anymore. We have f of negative x, which means every x in f of x, all these x's here, I have to replace it with negative x. So for our x to the 6, it's going to be negative x to the 6 minus 2 times negative x to the 5th. Plus 3 times negative x to the 4th. Minus 10 times negative x cubed. Minus 6 times negative x squared. Minus 8 times negative x. Minus 8, because we have to replace every x in f of x with negative x. We're replacing each of these terms with negative x. Just in case. We kind of questions on what we've done so far. Any questions on how we set this up? Anybody not looking forward to figuring out what negative x to the 6th is? And the interesting thing is simplifying each one of these is easier than you might think. Because if we look at negative x to the 6th, we're doing two things. We're multiplying a negative by itself 6 times, and we're multiplying x by itself 6 times. So I'm going to get a new page. You don't have to write this down. Because when we say negative x to the 6th, 1, 2, 3, 4, 5. Really, we're saying we're multiplying negative x by itself 6 times, yes? Well, negative x times negative x. Let's do this here. Because I have a negative times a negative, which is a what? Positive. Okay, times a negative. Makes it negative. Times a negative is, in fact, positive. Times a negative makes it, because we knew that was squaring. When we multiply a negative by itself an even number of times, it becomes positive. If we multiply it by an odd number of times, it becomes negative, yes? So just looking at this here, even number of times, it means this is going to be positive, yes? We'd have positive x to the what? If it's even, it's going to stay positive. If it's odd, it's going to become negative, yes? Okay. With that bit, let's look at this here. Well, we already figured out the first one. Negative x to the 6th is just x to the 6th. Our next one is negative 2 times negative x to the 5th. Well, the negative x to the 5th, part of this, well, we'll still have x to the 5th. We're still multiplying x by itself 5 times, yes? But that means it's going to become what? Negative. It's going to keep that negative with it, yes? And we're multiplying it by what? Negative 2. What's a negative times that negative? So really with this here, we went from, with the x to the 6th term, it was positive, it stayed positive, yes? With a negative, if it was negative, it's going to become positive. And if for that odd term it was positive, it's going to become negative because we're adding a negative to it. Because negative x to the 5th, well, 1, 2, 3, 4, 5, because we have, that's going to make it positive, negative, positive, negative x to the 5th. If I take that negative x to the 5th and multiply it by a negative 2, well, this negative and negative is going to make a positive 2 x to the 5th. You all kind of see how that works. Yes? There's a whole bunch of negatives. Now, I'm going to change it. If I said it was 2 times negative x to the 5th, it will be 2 times negative x to the 5th, which makes it negative 2. So if that exponent is odd, we change the sign. If the exponent is even, we leave it alone. So if we look at this here, since the second one was to the 5th power with that x, it means the sign has to change. If we look at the next one, the power is what? 4, which is even. So it means it's going to be x to the 4th, but we leave the sign alone. It's going to be positive x to the 4th. Our positive 3 times our positive x to the 4th is going to be 3x to the 4th. Our next exponent is 3, so it's odd, which means we're going to need to flip that sign from negative to positive. Or if it was positive, it's going to become negative. Our one after that is our x squared, another even. So we keep our sign, giving us negative 6x squared. Because the next one's kind of nice after that. Negative 8 times negative x. Negative times a negative is a positive, so plus 8x minus 8. And now we do it again. Now we actually count the sign changes. So from our x to the 6th to x to the 5th, it goes from positive to positive. So does the sign change? No. How about x to the 5th to x to the 4th? No, positive to positive. X to the 4th to x cubed? No, positive to positive. X cubed to x squared?
Yes.
Yeah. First one, we go from positive to negative. Then from x squared to x?
Yes.
Yes. And x to constant? Yep. So the number of negatives we have is 3, or an even number less than it. So we just subtract 2 till we can't anymore. So we could have 3 or 1. Questions on how we found the possible number of positives and negatives? We feel okay with that? I would also ask for the complex or imaginary, yes? Okay. This is actually, we're going to make a table to list our answers. Positive, negative, complex. So the most positive number solutions we could have was what? 3, yes? The most negative numbers we could have is 3. What was the degree? How many solutions can we have? If I have 3 positives and 3 negatives, do I have all the solutions? Yeah. So the number of complex is 0 because all are accounted for. Now at this point here, we need to find every possible arrangement of these numbers. And the easiest way I've found to do this is I start with the negatives. And I keep subtracting 2, because we can always have 2 less. So if we subtract 2 from 3, for the negatives we have what? 1. So the next possible set of solutions is I can have 3 positives and 1 negative, which gives us a total of what? 4. But how many solutions should we have? 6. How many am I missing? So those other 2 have to be complex. Because we need a total of 6 solutions. If I have 3 positive, 1 negative, the other 2 have to be complex. Questions on this here? We kind of get this here, yes? All right. The next thing I would do is take 2 away from the negatives. Well, that would take it from 1 to what? Negative 1. We can't have a negative 1 group of numbers. So whenever I can't take any more away from this middle column, I reset it back to the maximum, because we can have at most 3, yes? I take 1 group away from the positives. So 1 group away from the positives would make it 1. Because really what we're doing is finding every possible combination of 3 positives with our negatives. Once we find those, we take 1 of the groups away. Now I'm going to find every possible group of positive 1 group of positive numbers with our negatives. Well, 1 positive and 3 negatives give us a total of 4, so we're missing how many? 2. And we repeat this process again, because we can again take away 2 from our 3, which gives us 1. So I could also have 1 positive, 1 negative, which gives us a total of 2. How many are we missing? 4. Okay. Can we take any more away from our negatives? No, because 3 and 1 were the only option. I can't take any more groups away from the positive amount. So these here are all the possible combinations of positive, negative, and complex numbers we can have. That's it. Do we feel like this theorem had to have a little more to it than just this? Yeah. I did have a student, I think it was last year or the year before, point out and with most of these here, once I find the positives, for the most part, I know the negatives, because the total has to be what? 6. I haven't found too many, or I haven't found an equation yet that didn't do that, start out with 6. There are some, but it's few and far between. Questions on what we did here? All right. Positive, negative. I put these out here to the side just to remind myself what my maximum number of positive and negative are. So for positive, all we've got to do is come here and count the number of sign changes as we go through this here, from the 6th to the 5th to the 4th to the 3rd to squared x to constant. Now, if one of those is missing, we don't add it back in. We just count. From our 6th to the 5th, it goes from positive to negative. From our 5th to the 4th, it goes from negative to negative. So it doesn't change. From our 4th to the 3rd, we go from negative to positive. From our 3rd power to our square, we go from positive to positive, so it doesn't change. From our x squared to x, positive to positive. And from our x to negative 9, we get our 3rd change. So how many positives do we have? 3. Or an even number less than that. So 1. Questions on this here? All right. Now we need to find f of negative x. Now, as we kind of saw with the last one, if the exponent's even, the sign stays the same. If the exponent's odd, the sign's going to change. So for our 2 times negative x to the 6th, this would end up just being 2x to the 6th. The sign for the 2 is going to stay the same because the exponent is even. Our next one is negative 5 times negative x to the 5th. Odd power means the sign is going to go from negative to positive. It's going to change. So we have plus 5x to the 5th. Next one, the power is even, so the sign for 3 is going to stay negative, so negative 3. X to the 4th. Our next one, we have an odd power, so the sign is going to change to negative 3x cubed. Our 10 is going to stay positive because the x is being squared, even power, so plus 10x squared. What do we do about the negative x? Plus negative x. What's the exponent? Well, also, do we have an exponent really to contend with? No, so we can really just what? Drop the exponent, simplify. And if we're plussing a negative, it's just minus x minus 9. Yeah, that one's the one that's tricky because we don't have one written there. But if we did write it there, it would be 1. 1's odd. We change the sign. And again, we can count the sign changes. From x to the 5th, so positive to positive, so there is no sign change. Positive to negative, that's our first. Then we have negative to negative, which doesn't change. Negative to positive, this gives us our second. Then we have positive to negative, which gives us our third. And then our last one does not. So the most negatives we can have is 3. And funny enough, our solution for this one's almost going to be, well, not almost, it is going to be the exact same as the last one for our possible number of positive negatives in complex. Questions on anything we've done so far before we set this table up? So what's the most we can have of each? 3, because we found that we could have 3 positives or 3 negatives. Since the degree is 6, if we have 3 and 3, we have all of them, so we don't have any complex. Now the next one I would do is I would take 2, because our even amount away from negatives, because we could have 3 positives and 1 negative, which leaves me with how many complex? 2. Then I'd take another even amount from the negatives. Well, we can't, because we'd go below 0, which means I would reset the negatives to its max amount and take 1 even amount away from the positive, which means we could have 1 positive and 3 negatives, giving us a total of 4, which means we would have 2 complex. And lastly, we could have 1, 1, leaving us with 4. Questions on this here? And if you're wondering, yes, the number of complex is always going to be 0, 2, 4, 6, 8. It's going to be an even amount, except for 0, but yes. We're always going to be increasing or have some multiple of 2. Questions on this here? So we kind of get what's going on or how this works. Now, this seems like an odd concept, but again, if we're trying to find possible zeros, we have no starting point. This, with the rational zeros theorem, help. Here. So, okay, yeah, so the question is, we get how we go from here to here and then go from this set to this set. But what I'm really doing is I keep subtracting 2 from the negatives till I can't. So we did 3 minus 2 is 1, because I can have 1 group. If I subtract 2 again from 1, we get negative 1. I can't have negative 1 possible negative solutions. I can't just have that amount. So what I do from here is I reset it to the total amount. Because this, 3 and 3, 3 and 1, is every possible positive 3 solutions with our negative groups. So from here, I reset the negatives back to the total amount. And then take 1 group away from the positives. Now we're seeing every combination of 1 positive solution with all of our negatives. Or another way to look at this. So positive solutions we found is 3, or an even number less than it, which would be 1, yes? So for positives, I can have 3 with our negatives. Now negatives, we can have what here? 3 or 1, yes? So for negatives, I could have 3 positives, 3 negatives, or 3 positives and 1. That's how we got those first 2. Does that make sense? But with the positive groups, I could also have 1 positive. But that's still going to connect. I could have 1 positive and 3 negatives, or 1 positive and 1 negative. So we're just listing out. And what I'm doing with these groups is I'm starting out with 3 positives and going through every possible negative first. Let's get a highlighter. So essentially that's what we've done with this here and filled in the missing for the complex. And then I went from, well, I don't have any more groups of 3 positives, so I'm going to move to 1 positive. And then assign it to every possible group of negatives, which there's only 2. is how we got that there. Does that kind of make sense? Let's just make up a hypothetical one. Let's say that the number of positives is 7 and the number of negatives is 6. Which means our total is 13. So we don't have an equation with it, but positive, negatives, complex. So we'd have 7, 6, 0. Or we could have 7 positives and 4, because I'm taking the other option for our negatives. Yes? 7, 4 is 11, so we're missing 2. Or instead of this, page, we could have 7 positives, 2 negatives, and 4 complex. I can take 2 away again. 2 minus 2 is what? 0. It might seem like we can't have 0, but we've had problems where we didn't have any positive or negative. We can have 0. So the 4 here.
6 minus 2
2.
equals 4.
Yeah. So I'm just so the 4, the middle group, I just keep taking those groups away. So I have every combination of 7 positives in every negative group. And the complex is just what's missing. Now, looking at this here, do I have any more negatives that I can match with positive? No. So I move on to the next possible positive amount, which would be 5, because we take 2 away from the positives.
Oh.
And we do this again, so it'd be 2 or 5, 6. Because 6 is our max, so it's almost, we reset the negatives with the next amount of positives we can have. Well, 5 and 6 is 11, so we're missing 2. Then we'd have 5 and do the process again. Just keep taking 2 away from the negatives. 5 and 4 is 9, so we're missing 4. So that's starting to, and then it would be 5 and what? 2, leaving us with 6, and then 5, 0, 8. Can't take any away from the negatives. So we'd do it again. We'd have 5, or not 5. Because if we take 2 away from 5, our next possible positive numbers or set of positive numbers is 3, 6, which is 9, so we'd have 4. Then we'd have 3, 4, 6, 3, 2, 8, 3, 0, 10. Then we do 3 minus, so take another 2 away, so we'd have 1, 6, so because that's 7, we're trying to get to 13, so we'd have 6, and we'd have 1, 4, 8, 1, 2, 10, or 1, 0, 12. So it's just that same process repeated, because once we get the max values, we just keep I keep subtracting 2 from the middle to see that many group of positive with that many negative. Does that kind of make? Now this is an extreme. We won't have anything that big, but that's kind of what we're doing with these. Does that make sense? And any of those rows going across is never going to be more than the degree. So here, the number of positive, negative, and complex will never be more than 4. Questions on this here? Again, it's one of those things that's simple and complex all at the same time. Okay. Yes. Because if we count this here, x to the 4th to x to the 3rd is 1. Positive to negative. Then we have negative, positive, positive, negative. So the number of possible positive is 4 or less than it. Yes. We don't even have to find the negative. Now, I think most of y'all are, I mean, you get rewriting it out with f of negative x in each one, yes? But what did we just say? If the exponent is even, the sign stays the same. If the exponent is odd, we flip it, yes? So let's look at this here. What's the first one's exponent? So it stays the same, so that would end up being 3x to the fourth, yes? The next one is odd, so we would change it from negative to positive 7x cubed. Plus x squared would say plus x squared because our exponent's even. No exponent with an x, so we have to change it to plus 13x. So we can fill back in that negative x, but if we know the exponent's even, it stays the same. If the exponent's odd, we change it. There's not a whole lot of reason for us to rewrite the negative x in each if we know what's going to happen. Positive, negative. The most positives we can have is 4. The most negatives we can have is 0. The degree is 4, so we need a total of 4. We have all 4, so the number complex is 0. Since we can't take any away from the negatives this time, we're end up just going to take them away from the positives because we can have 4 positives, 0 negative, 0 complex. Or we can have 2 positives, 0 negative, and 2 complex. Or I can have 0 negative, 0 positive, and 4 complex. Can't take any more away from the negatives. Well, we can't take any away from the negative group to begin with. We've taken them all away from the positives, so this is all the possible arrangements. Yes. Questions on this here? Now, with any of this, let's get this. I'm just making this graph up. This is 100% not going to be the graph of this function here. But let's imagine, so you graph this and this is the function you got, yes? So according to Descartes' rule of signs, the number of possible positive solutions has to be 4, 2, or 0, yes? If I look at this graph here, well, I have 1, 2, 3 positive solutions here, yes? So according to this chart, well, 0, 0, 4 is not going to work because I definitely got more than 1 positive. But we actually got more than 2. So the only possible arrangement is 4 positive, 0 negative, and 0 complex, yes? Is there a fourth positive 0 that's shown up here? No, but what does that tell me? It tells me that somewhere over here, the graph is going to have to come back up and give me that positive value. Does that make sense? It gives us an idea, an understanding of what's going to happen. Even though I can't see it in this small window, I know that there has to be another positive 0 out there. And we're going to find it. Or it could be, I have, if it only had 2, there's a good chance there's either 2 complex or there's not. So if we had this here, I have it crossing twice, so I know that there's 2 positives. There's a good chance it's either going to be 2 negative or 2 more positives, or 2 complex or 2 positives. It gives me an idea of what I'm looking for. Or where we had 1 negative, 4 complex, or 4 positives. It gives us an idea so we're not just hunting for values. We can actually narrow our window down. But I'm going to bore you with the rest of those. That is it. Now, And that is the end for chapter 4. So we're done with this here.